Hey everybody, welcome back to the channel. Today we're going to take a quick look at this homemade Tesla coil winding machine. And we're also going to take a look at measuring the performance characteristics of a secondary coil. Hobbyists would call these Tesla coils. In literature, you'd refer to them as a quarter wavelength helical resonator because they basically take a standing wave and resonate. So one of the most important parameters you really care about is resonant frequency, but also the Q factor of the coil, which is how much voltage gain does that coil give you, and it's something that's not really discussed enough in the Tesla coil community. So starting out looking at the winder, it's pretty much all stuff from the hardware store on Amazon, just a wood base, some threaded rods for holding your wire, which this spools from this coil. And then as you can see here, I have some laser cut hardboard, which has different hole sizes. So you can put screws through it to hold your coil in place. And it's all adjustable for common sizes of PVC, cardboard, coil, tubes, etc. And if you don't have a size that's about perfect, well, then you end up with just wrapping with some tape or some rubber bands or something along those lines to get it perfect. We also have a simple motor and pulley system. This is from Amazon. Ideally, you would hook this up to like a variable power supply, and then I have a switch for forward and reverse. It takes the act of putting 600 to 1,000 turns of wire on a coil from something that would be incredibly painful to do manually and makes it significantly easier to do in a half an hour or 45 minutes. There's much more elegant systems online, but for someone that makes a coil maybe every once a couple of years, this is more than adequate. So winding the coil is as simple as starting out with a few turns on one end near where you want the coil to start. I use Kapton tape. Painter's tape works really great. And then starting to guide that coil with your finger, making sure that each winding is right next to the previous winding. I find a nice trick is to put a piece of Kapton tape on your finger so the wire glides nicely under it.
Now once you get going, it's pretty mindless. Unfortunately, this is about one rotation a second, so to put 500, 600, 700 turns on a coil, this is still going to take a little while.
It's also a good idea if you have to stop winding at any time to have a few spare pieces of tape. That way you can stop, put the tape down, and your winding doesn't unspool itself, which is a huge pain to fix. As you can see here, we walk our way through the cable. I took a couple breaks because holding your finger in place like that for even 30 minutes is painful.
Here we have the finished winding with tape holding both ends of the wire in place still. Next, we're going to drill holes in the coil to terminate the wires. In this case, I'm going to drill without anything supporting it on the coil form, but if you were making a larger hole, you'd want to support it with a wood backing or something so the plastic doesn't crack. Then we're going to measure the uncoated coil on the coil form to look at its Q and resonant frequency. Unfortunately, I'm recording this after the fact. It seems like measuring that on the coil form with the metal rod going through it resulted in altering the measurements quite a bit, which thinking about it now is not surprising.
So for testing this, it's really easy just to take a signal generator, set up a sweep pattern, and then look at your oscilloscope, and wherever you have a peak, that's going to be your first resonant frequency. You'll typically have a second peak at almost double that, and that is your half wave resonant frequency. So it's interesting because you could actually ground the top of the coil at that frequency and still have resonance. And there's actually a small field of study, something I did in college, called Bi-modal quarter wavelength helical resonators, and the idea is for like lightning testing. Once your coil is resonating at the quarter wavelength, when you have that breakdown, that arc forms, it detunes your coil because now that top part is essentially being connected to ground. So there's this idea if you drive two resonant frequencies, one for the quarter wavelength, one for the half wavelength at the same time, once that arc is formed, you can sustain that arc longer and you can pump a lot more energy through it. At which point the winding is mostly done. Then you want to protect that coil for two reasons. One, physical protection, but two, insulation. Again, much easier to do that when you're on a winding system like this. So we're going to paint it with a polyacrylic. Polyurethane, like high gloss, is stronger. It's a more durable coating, but it also has a yellow tint. So when I'm winding on like white colored tubes, I prefer polyacrylic because it's clear. This is a nice matte finish. I think it looks nice, doesn't protect quite as well, but I also don't really take these coils out traveling or doing activities where they really need significantly better physical protection. So that holds the coil onto the form, and it also adds additional layers of polymer so you don't have a breakdown. If you have high voltage breaking down on the coil form, it's not great. It'll start your cardboard on fire, and it also makes it significantly less exciting to watch when it's not coming out the top where you expect it to. The second half of this video, talking about coil performance parameters, we'll take this coil that I just made and we're going to measure it for its frequency and its Q factor to see how good of a coil it is. Why are we doing that? Well, I found out many years ago that winding cardboard tube coils ends up with a terrible Q and a really bad voltage gain, and plastic cores are significantly better. So ever since then, it's something I pay really close attention to. Q is basically the quality factor of a coil, and it is directly proportional to the voltage gain. So if you put a standing wave in a coil, the peak voltage of that standing wave, just multiply it by the Q factor of the coil, and that's how much voltage you'd expect to have standing on the high side of that coil. Now, when you load it, that Q is going to end up being a little less, and as soon as that breakdown happens, your coil is detuned. So your absolute calculations, it's probably going to end up being less than that, but it gives you an idea, especially to compare different coil formers, like for instance this cardboard that has a Q of about 8, to this plastic tube, unknown type of plastic, that is a Q of about 150, as we're going to see quickly here.
Okay, taking a look at this coil with a few layers of polyacrylic on it, what we have here is a setup to measure the both resonant frequency and the Q factor of that coil. It's pretty straightforward. I have just a piece of wire, happens to be 2 pieces of wire, attached to an oscilloscope probe to act as an antenna. It's a little close to the coil for this video, but I wanted it all to be in the frame. That is then attached to a signal generator that's sweeping, in this case, from 450 to 480 kilohertz. And I'm looking at the entire sweep time here. And what that allows you to do then is use the time and time deltas on the cursor, and you can do some basic math to figure out the exact frequency of those different points. So how am I calculating Q? Pretty straightforward. It's essentially what's called the 3 dB bandwidth over the resonant frequency. So the resonant frequency is that center point. The 3 dB bandwidth is when the signal drops from that peak 3 dB, which is 0.707 of the peak. Where are we at? So I'm just measuring the distance between those two lines, which turns out to be approximately 2 point some kilohertz. And we have a resonant frequency of about 465 centered here. So our Q ends up being 190, which is actually pretty good. I'm really happy with that Q. And you can tell immediately it's a high Q coil just because as you notice how I get closer to the coil here, it starts detuning it. And anyone that's ever old enough to have been around a radio or an analog TV, this is exactly what happens to that tuned RF receiver circuit as you approach the antenna. Well, thanks for watching, everybody. Hopefully you found the coil winder inspirational and learned something about testing coils for their Q and resonant frequency. Remember to subscribe if you like this kind of content, and let me know in the comments what you think.